right, so today we're going to learn how to graph things using calculus, and I say learn, but really we already learned all the information that we need. We've already been graphing polynomials with our calculus. Now we're just going to learn how to graph more complicated functions, but it's the same exact procedure, so it should not be too bad. This particular video, I'm going to give you an outline of steps you should follow in order to graph functions using calculus, and then we're going to do just one example, but in real thorough detail. These examples tend to take a long time, so one example will be enough, because otherwise this video is going to be terribly long. If you happen to be one of my current students, you can also go on our Moodle page, and there will be another couple of examples worked out in the notes on Moodle. All right, so we are doing today graphing with calculus. And here's a general outline of how you should go about these graphing problems. The very first thing that you should always do, find the domain of your function. Now, when we were just graphing polynomials, we didn't really do this, but that's because polynomials have domain all real numbers. Now we could have more complicated functions, maybe rational functions where we divide by other polynomials. You know, then you could possibly divide by 0, so we got to find the domain to make sure we're okay. After you find the domain, find all of your intercepts. To do that, remember that a y-intercept occurs when x is equal to 0, and x-intercepts occur when y is equal to 0. Now, finding your y-intercept is usually pretty easy, just plugging a 0 in for x and you get an answer. Finding the x-intercept is sometimes a little bit difficult. So I would suggest you try to do it, but if the problem is really terrible to solve, you can skip it. But in general, you should try to find those x-intercepts because it will make your graph much more accurate. Okay. After we have our intercepts, well, I'm going to put this step in parentheses. Finding symmetry. So symmetry, we're just talking about, is the function even or odd or periodic? That will make it so that, you know, if it's even, you can reflect it across the y-axis and the graph looks exactly the same. If it's odd, it's across the diagonal x equals y line. And if it's periodic, like our trig functions, it's going to repeat. But I'll be completely honest, I tend to skip this step because if you do all of the other steps, the symmetry takes care of itself. So I usually do not bother doing that. After that, we need to find all of our asymptotes. So remember, your vertical asymptotes are where you've divided by 0. So it's very good that we already found the domain in step 1 because you're probably going to need that when finding your vertical asymptotes. For your horizontal asymptotes, remember that's talking about the end behavior of our function. We have to do a limit as x approaches infinity, and also a limit as x approaches negative infinity. Well, a lot of the times you get the same answer for both going towards infinity and negative infinity, but you should still check it because there are functions out there that behave differently on both sides. So always double check. There are also slant asymptotes, but those don't happen as often. You probably remember slant asymptotes from your pre-calc classes. When those come up, that is when the numerator has degree that is exactly 1 bigger than the degree of the denominator. And you would find your slant asymptote by doing polynomial long division. I'd tell you not to worry too much about that because in general, we're not dealing with those problems in this particular class. We just have a lot of vertical and horizontal asymptotes. All right, so after all the asymptotes are found, that's when we get to move on to using derivatives. So step 5 is find where we increase. So we'll find where the function is increasing or decreasing. And also find your relative or local extrema. So some textbooks refer to this as a relative extrema, relative maximum, relative minimum, and other books call it local extremum, which would be your local maximum and local minimum. Doesn't matter whether you use relative or local, they're the exact same thing. That's just the preference of your author for your book. Finding where the function's increasing or decreasing, that is using the first derivative. Remember that our function is increasing when the derivative is positive, and it's decreasing when the derivative is negative. That's due to the fact that the derivative gives us the slope of the tangent line to our original function. Step 6, we need to find where the function is concave up, which I abbreviate as CCU, or concave down, which I say CCD, and we need to find inflection points. So finding the concavity of our function and finding the inflection points, that uses the second derivative. Remember, you take your second derivative, find where it's 0 or undefined, and then we check values to see where the second derivative is positive and where it's negative. If your second derivative is positive, you get something concave up. So positive, you get concave up like a cup. Negative, you get concave down like a frown. After that point, once we found where it's increasing and decreasing, concave up and concave down, also our inflection points, which remember that's a point where we change from being concave up to concave down or the other way around, then you're finally ready to sketch the graph. So that's step 7, sketch. And to sketch it, I suggest you first put all of the points you found on the graph, mark where your asymptotes are with dashed lines, and then use all of your increasing and decreasing and concavity intervals to just graph a general shape of what's going on. We're not really looking for the most perfect graph in the world here. We're just looking to have an idea of what the curve looks like. How does it bend? Where does it go? Doesn't need to be perfect, but the derivatives will give us a very nice idea of what the graph looks like. All right, you guys ready to graph? We have one example today, and I know it sounds crazy to only have one example, but these things take forever to explain. But it's much quicker when you're doing it on your own because you don't have to talk through each step. But one example done very, very thoroughly should help you understand what's going on here. So we are going to sketch the function y equals 2x squared over x squared minus 1. And remember, the very, very first thing that we want to do is find the domain of this function. This is a rational function. I have a polynomial on the top and a polynomial on the bottom. Our only danger in this problem is we could be dividing by 0. So we need to make sure we don't divide by 0. We need to find those values to make sure we exclude them from our domain. So when finding your domain, on this problem, I'm going to take my denominator and set it equal to 0. When I solve this equation here, that will give me all of the values that are not in my domain. So when I solve this, we can solve it by factoring, or we can solve it by adding the 1 to the other side. I would actually suggest you solve it by factoring, because there are far too many students out there that when they add to the other side and take a square root, they forget that plus or minus. So I'm going to do this by factoring, because then I don't have to worry about missing that plus or minus. Factors as x minus 1 times x plus 1. This first guy gives me x equals 1 as a solution. And the second guy gives me x equals -1 as a solution. Remember, those are the values that are not included in my domain. So this means that my domain is all real numbers except ±1. But every single other number I can plug into this equation and get an answer. So we're all good. So that's my domain. The next step is to find my intercepts. And I'm just going to make a little box over here on the side, keep a running total of all the things we find, because I'm going to forget the things we did at the beginning by the time we get to the graphing point. So let me write down my domain is all reals except ±1. All right. Now let's go ahead and find our intercepts. I usually start by finding my y-intercept because that's a little bit easier most of the time. Remember, your y-intercept is when you plug in x equals 0. So to find my y-intercept, I plug in x equals 0. And I get that y is going to be equal to 0 over -1, which is 0. This means that my y-intercept is the point 0, 0. To find my x-intercepts, that's where your entire equation is equal to 0. It's when y is equal to 0. To solve this equation, we'd multiply both sides by the denominator and get 0 equals 2x squared, which means x is 0. Shouldn't be a surprise because honestly, when we found our y-intercept, it already told you this is also an x-intercept. You still should check because it's possible to have more than one x-intercept, so it's always good to double check. But I found out that I only have one intercept in general, the point 0, 0. It's both my x and my y-intercept. All right, so the next step on our list was to look at the symmetry, but again, I tend to not do that. Just to give you an idea though, this is an even function. If you plug a -x into this equation, you're going to get the same exact thing out. The reason for that is because -x squared is still going to be +x squared. And same here. I'm going to get the exact same thing. This just means that if I look at my graph when I'm finished, it's going to look completely identical on the left and on the right side of that graph. All right. So now let me find my asymptotes. And I just completely erased the whole problem that I'm doing. That wasn't very smart, but let me quickly write it back down. We had a 2x squared over an x squared minus 1. That's what we were graphing. All right, so for the asymptotes, I always start with my vertical asymptote because most of us are more familiar with that. Your vertical asymptote occurs at places where we divide by 0. So that would be when x squared minus 1 is equal to 0. Well, we already solved that. We solved that when finding our domain. So this tells me when x is +1 or -1, I have a vertical asymptote. So that's a vertical line that my graph does not touch. So vertical asymptote, x is ±1. And then horizontal asymptote, that's the one that involves limits. I need a limit as x approaches infinity of my function. I have a 2x squared over an x squared minus 1. And some of you probably know the answer to this right away, but I'm going to remind us how to do limits to infinity the way we learned it before we even learned L'Hopital's rule, just to make sure you don't forget your old techniques. I have to take the term with the highest exponent from the denominator and divide every single thing in the problem by that term. So this limit is equal to 2x squared over x squared and x squared over x squared minus 1 over x squared. Divide everything by that x squared and simplify. When I simplify, I have a 2 on the top and 1 minus 1 over x squared on the bottom. And now let's see what happens when I plug in bigger and bigger numbers for x. So x going to infinity. 1 divided by a really, really huge number, that goes to 0. So I have 2 divided by 1, which is 2. This tells me I have a horizontal asymptote at y equals 2 on the right side of my graph because I was approaching positive infinity. Now, we should double check what would happen if I was approaching negative infinity instead, because what if I have a different horizontal asymptote on the left side of my graph? Well, luckily, if I just think about this being a negative infinity instead of positive infinity, all of the work would be the same. I divide everything by the highest exponent from the denominator, I simplify, and then as x approaches negative infinity, this little fraction here still goes to 0, and I still get an answer of 2. That's very, very common. It's very normal to have the same horizontal asymptote on both sides, but you should take a quick look to double check just in case you have a really special function where it's a little bit different. All right, so I have my domain, I have all my intercepts, I have vertical and horizontal asymptotes, and now we're ready to figure out where we're increasing or decreasing by looking at the derivative of our function. So for increasing and decreasing, and our relative extrema, we need to look at the first derivative of my function. Well, look at our function here. It's a quotient, so I'm going to need the quotient rule to find this derivative. My quotient rule says that the derivative is equal to low d high minus high d low, square the bottom, and away we go. Just remember, doing quotient rule, each time I say low, I'm referring to the denominator. Each time I say high, it's the numerator. And when I say d in front of it, I'm talking about the derivative. So the only pieces I have left to fill in here are low d high, high d low. So I need to do the derivative of the top and the derivative of the bottom. My d high, derivative of the top, is 4x. D low, derivative of the bottom, is 2x. All right, so those of you who are actually my current students know that I'm not a very big fan of simplifying my answers because I'm just too lazy to do it most of the time. But on problems like this, where we're going to have to then find where we're increasing or decreasing, I suggest that you simplify it. To simplify, we're going to want to distribute everything that we possibly can, but only in the numerator. And I was just about to ask you guys, why are you not yelling at me that I forgot to put my square down at the bottom? But then I remember you're not actually watching this live, so nobody can catch my mistakes. But luckily, I noticed before we moved on. So remember that in your quotient rule, you have to square the bottom. So I need that squared right there. All right, distributing on the top, I'm going to distribute this and get a 4x to the third and a minus 4x. And then this guy is a minus 4x to the third. And on my denominator, I still have x squared minus 1 squared. Now look at that. On the top, my 4x cubed and my negative 4x cubed, they subtract away to 0. So I'm actually going to get a much simpler derivative to look at, which is why I suggest that you simplify these. So when I combine my like terms on the top, I just have negative 4x divided by x squared minus 1 squared. And that is my simplified derivative. so now I need to figure out where am I increasing and where am I decreasing. To do that, the first thing we need is to find our critical values. Those are where the derivative equals 0 or where it's undefined. So first, let's find where it's undefined. My derivative is undefined when I divide by 0. And when I divide by 0, that means my x is +1 or -1, those values that weren't in my domain. And to find where my derivative is equal to 0, we would take my entire derivative and set it equal to 0. But when you have a fraction equaling 0, it equals 0 when the numerator equals 0. Remember, if you forget that, you can always set the whole thing equal to 0, but your first step would then to be multiplied by the denominator, and it's going to cancel out anyway. So y prime equals 0 when my top, -4x, is equal to 0. And that happens when x is 0. Now, some books specify a different name for when you have your derivative equaling 0 or your derivative undefined. They're all critical values, but certain books refer to these values where the derivative is 0 as stationary points. So if you're using one of those books where they refer to stationary points, that's what they're talking about, when the derivative is equal to 0. So I have critical values at ±1 and at 0, but this guy here is in my domain. I'm going to eventually need to find the y coordinate of this point so I can put it on my graph. What we're going to do first, though, now that I have my critical values, I'm going to put all of my critical values on a number line. We had -1, 0, and 1. And I'm going to point out this -1 and +1 were my vertical asymptotes. This guy in the middle, 0, is the only one that has a hope of being a relative minimum or a relative maximum. All right, so now that we have our number line, we figure out where we're increasing or decreasing by checking values in each section of the number line. So I'm going to start by checking what happens with -2. I'm going to be plugging this -2 into my derivative and finding out if it's positive or negative. Remember, we don't actually care what the value is. We only care if it's positive or negative. So take a look at this derivative. My denominator is something squared. When you square something, it's going to be positive. The only time that when I square something it's not going to be positive when working with real numbers is if I square 0. But my denominator is not going to be 0 because then I'd be dividing by 0 and we know that that's a bad thing. So when I'm figuring out if my entire derivative is positive or negative, I can figure that out by just looking at the numerator in this particular problem because the denominator will always be positive. So if I plug -2 into the numerator, -4 times -2 is positive, and that means that my function is increasing in that section. So now if I plug in a value between -1 and 0, I guess I'll use -1/2. Again, if I plug this -1/2 into here, -4 times -1/2 is positive, and I'm still increasing. Now let me try +1/2. If I plug a positive value into this numerator, I get something negative, so I'm decreasing. And again, if I plug in this +2, I'm still going to get negative and decreasing. Now be careful. A lot of people are going to be tempted to say that we're increasing all the way from -infinity until 0. But remember, this guy right here, -1, is a vertical asymptote. It's possible that I could be increasing and going up to infinity on one side and increasing on the other side, but starting down at the bottom of the graph. So we should list these two intervals separately just to be safe. So I'm increasing on negative infinity to negative 1, and again from negative 1 to 0. And, I'm sorry, there's a spot on the board right there. So that makes it a little hard to read. I'll put that right here, negative 1 to 0. And I'm going to be decreasing from 0 to 1, and again from 1 to infinity. All right, so we have a lot of information for our graph right now, but we still need to do the next step of finding the second derivative to figure out where we're concave up or concave down. All right, so for concave up and concave down, we need the second derivative. I have my first derivative right there. To get my second derivative, we have to use a quotient rule again. And to do the derivative of the bottom, I need a chain rule. So we have to be very careful. This is a more complicated derivative. My quotient rule says that we're going to have low d high minus high d low, square the bottom, and away we go. So derivative of the top is negative 4. That's not too terrible. But for this d low, the derivative of the bottom, that's the chain rule. So I'm going to have my 2 come down. My new exponent is a 1. And then I have to multiply by the derivative of the inside function, which will get me a 2x. And now we have that giant mess of a derivative. I would suggest before distributing everything to try to simplify, first take a look at what we have. I have an x squared minus 1 to a power over here. I have an x squared minus 1 over here. And I have x squared minus 1 to a power in the denominator. We can do a little bit of cancellation. The lowest power of x squared minus 1 is this guy, x squared minus 1 to the first. So that's all that I'm allowed to cancel out. So I can cancel x squared minus 1. One of those guys goes away, and 1 in the denominator goes away. So I have just 3 left down in the denominator. So let me rewrite that with our cancellation. I have an x squared minus 1 times a negative 4. And then minus a negative is going to make this positive. 4 times 2 is 16. X times x is x squared. All divided by x squared minus 1 to the third. So it's still ugly, but it's a little bit better than what we had before. So now I would distribute and combine like terms on the top. So my denominator is still going to be x squared minus 1 to the third. And for my numerator, I'm going to have negative 4 times x squared. That's negative 4x squared. And I can combine it with my 16x squared to get 12x squared. And my negative 4 times negative 1 is positive 4. So that is my second derivative. All right, so now we have to remember, why did I even find the second derivative in the first place? And that was to figure out where we're concave up or concave down and find our inflection points. So I need to figure out where my second derivative is equal to 0 and where it's undefined. So let's do the undefined first. It's undefined when my denominator is equal to 0. And luckily, that's still at x equals plus or minus 1. Those are our vertical asymptotes. This should not be a surprise. That happens a lot when doing these problems. Now, where is my second derivative equal to 0? Well, the second derivative equals 0 when the numerator equals 0. And if I try to solve this guy, I subtract 4, divide by 12, and then you would try to take a square root. But I'd be taking a square root of a negative number. And in calculus, we work with the real number system, so we are not allowed to take square roots of negatives. We only do that with complex numbers. So this tells me no real solution for where my second derivative is 0. So the only values that are going to be going on my number line are plus or minus 1. So let me put a number line on here. There's -1, there's +1. And I know it's a little bit cluttered, but I didn't want to erase the second derivative because I need that to figure out where we're positive or negative. So I'm going to use my second derivative and plug in values in each section of my number line to see if my second derivative is positive or negative. I would suggest that you plug in -2, 0, and 2, but any numbers in those subintervals are okay. So let's take a look at what we got here. I have a 12x squared plus 4. No matter what I plug into that numerator, I'm going to have 12 times something that's either positive or 0 plus a 4. It's going to be a positive number. If I plug a positive in, it's positive times positive plus positive. If I plug a negative in, a negative squared is positive. So it's still positive times positive plus positive. And the only other option is if I plug a 0 in. Well, then that would get rid of 12x squared, and I'd still have a 4, which is still positive. So no matter what I plug in, my numerator on this problem happens to be positive. That means I can check these values just in the denominator to see if I get positive or negative. If I plug in -2 into the denominator, -2 squared is 4, -1 is 3, and that positive number to the third power is still positive. So I know I'm positive in this section, which means I'm concave up, like a cup. Now if I plug in 0, in the denominator, I'll have -1 to the third. That's going to be negative. So I've concave down, like a frown. And then when I plug in the 2, 2 squared is 4, -1 is 3, cube it, and it's still positive. Concave up, like a cup. All right, so let me put that information over on this side here. I'm concave up from -infinity to -1 and from 1 to infinity. And I'm concave down just between -1 and 1. All right, good. We can still see that over on the side. So now everything I have over on the side is everything I need to graph this function. So to graph the function, the very first thing that I would do is put all of the points on the graph that I possibly know. I don't know very many. The only point that I know is 0, 0. I am going to point out I didn't specifically say anything about the inflection points on that problem because the only places where my graph changed concavity were at my vertical asymptotes. That means it's not an inflection point because I don't have a point there. It only changed from concave up to concave down when we crossed a vertical asymptote. All right, so here's my only point that I know, 0, 0. And that might be a little terrifying. We're going to graph this whole function, but we only know one point. How are we going to do that? Well, don't freak out and just go ahead and put in all the info that we know. Put your vertical asymptotes on the graph. They're at -1 and +1. So I'm going to put my vertical asymptotes as a dashed yellow line on my graph. These are vertical lines that we cannot cross when we're graphing our function. All right, now let's put a horizontal asymptote. My horizontal asymptote is at y = 2. So that's at 2. And let me put a dashed horizontal line representing that horizontal asymptote. Okay, and now, believe it or not, we do have enough information to graph. Let's read our graph from left to right. What happens over here before I reach my vertical asymptote at -1? If I look at all my increasing and concavity information, I see that before I reach -1, I'm increasing and I'm concave up. There's only one place on this graph where I can put a curve that is increasing and concave up that matches my asymptotes. And that is right up here in the top corner. I can't put that same shape down here in the bottom because then it's not going to match my horizontal asymptote. So that's the only logical place to put this. Now I have to ask what happens between my vertical asymptote at -1 and my point at 0. Well, this says I'm still increasing between -1 and 0, and this tells me down here I'm concave down. So the only way that I can be increasing from my asymptote to my point is if I'm starting down here at the bottom of my graph. So I'm going to start down here at the bottom of my asymptote and increase, concave up, or sorry, concave down. Increase and concave down looks like half of a frown right there. Now, what happens between this point and my vertical asymptote at 1? Well, after I reach the point at 0, this tells me I'm going to start decreasing. And I'm still here in a concave down interval. So all that happens at this point is I switch to decreasing, still concave down, so I get the other half of my frown. Now we just have one piece left. What happens on the right side of this vertical asymptote? Well, after x equals 1, this tells me, let's see, this should be infinity. You guys should have yelled at me about that, except you don't have me to yell at. All right, so decreasing 1 to infinity. I'm going to be decreasing, and then I'm also going to be concave up. So decreasing and concave up, the only place that I can possibly put this is up here in the upper corner. That's the only way that I can match my asymptotes. If I were decreasing concave up down here, I don't match my horizontal asymptote, and that's a problem. Now, I would like to point out that that symmetry that we skipped earlier, if you look at this graph right now, we are symmetric about this y-axis. It is an even function. Notice that I have this mirroring that's going on, and just like I told you, it's going to take care of itself if you do all the other steps correctly. And this point right here, my point 0, 0, we now know for sure this is a relative maximum because that is a point that is higher than all other points near it. So this is the graph of our function. Takes a lot of work to get there, but honestly, I think it's easier graphing with derivatives than it is graphing all this stuff with pre-calc skills. Let me know if you think that too. If you have any questions for me, feel free to drop them down below. And if you happen to be in my classes currently, feel free to reach out to me and ask questions during my office hours or through email, whatever works for you. And I will be posting some more videos next week to continue our discussion on maximums and minimums. And we're going to get to some really complicated word problems next week. So make sure you come back to see more. I'll see you guys next time.